Now come to the next point, redistribution of charge and loss of energy during the process of redistribution of charge between the conductors. See, redistribution of charge between the conductors and loss of heat in this process. Loss of heat in this process. See here, what we will do here, we will take two conductors, have certain capacitance C1 and C2, and those two has been charged Q1 and Q2. Let these two conductors have capacitance C1 and C2. Charge on that is given as Q1 and Q2. And these two are kept very far away. Okay. So let two conductors of capacitance C1 and C2 charge Q1 and Q2 respectively, initially kept very far away. First of all, why we are keeping or putting this condition kept very far away? Because if these are come close to each other, so one of the conductor come into the influence of field of the other. So we are considering that these two are not in the effect of field of each other. These just like isolated conductors. So there is no effect on this conductor of field of this conductor. Similarly, there is no effect of field of this conductor on this conductor. They are simply isolated. Now, so because of this charge and capacitance, these have some potential. So potential of this here, so potential is your V1, this is your Q1 by C1. For this, potential V2, which is your Q2 by C2. So these two conductors are at different potential V1 and V2. Now, the question is that when these two conductors are connected with a conducting wire, then what happened? See, these are the, you can say, initial condition. Now these conductor which are having charge and capacitance C1, C2, these two are joined with a conducting wire. Important point, this is a conducting wire. Then what happened? So because of this conducting wire, or whenever two conductors are connected to each other or joined with a conducting wire, so charge flow between these two conductors. As we know, positive charge flow from higher potential to lower potential, but in fact positive charge never flow. What flow? Electrons. Electrons move from lower potential to higher potential, and that process will continue till both are not reaching at same potential. So here also same thing will happen. Same thing will happen. Some charge will flow from, or some electron will flow from this conductor to this conductor, or maybe this conductor to this conductor. That we don't know. So we can assume, let the final charge on this your Q1 dash and on this your Q2 dash. This is the final charge. So flow of charge will stop when both are at same potential. That can be said as a common potential. So how to make equation, or how to get what is the final charge Q1 and Q2 dash, and loss of heat means when electrons are flowing through the wire, so there is certain loss of energy because of the flow of charge. So that loss of energy we would like to calculate here, as well as we would like to calculate how much the final charge and how to solve such type of problem. The first concept here, first equation we can say by using conservation of charge. Conservation of charge concept. By using conservation of charge concept, whatever charge has flown from one conductor to another conductor, that will remain on these two conductors. So total charge or sum of the charge on these two conductors will remain constant. So initial charge on this was Q1 and Q2. Sum of the charge will be Q1 plus Q2. Final charge here Q1 dash and Q2 dash. So final charge plus a final charge equal to your initial charge. This equation can be said as the first equation. This is called your conservation of charge equation. Second, at steady state. At steady state means, or at electrical equilibrium, or at electrical equilibrium, flow of charge stop. Flow of charge stop. So both the conductors will be at same potential. Both the conductor will be at same potential. So that is called common potential. Called common potential. Okay. So V common, we can say Q1 dash by C1 is equal to your Q2 dash by C2. This is your second equation. Now we are having two equations, 1 and 2, and two unknowns, Q1 dash, Q2 dash. Just we can simplify from equation first and second. You can substitute the value of, suppose Q1 dash, the Q1 dash is your C1 by C2 Q2 dash, C1 by C2 Q2 dash. The Q2 dash will be your, so our Q1 dash is equal to Q2 dash, we can write C2 by C1. So this is your nothing, C1 by C1 plus C2 into Q1 plus Q2. Similarly, Q2 dash will be your C2 by C1 plus C2 into Q1 plus Q2. These are the value of final charge after connecting these two conductors with a conducting wire. So Q1 dash C1 by C1 plus C2 into Q1 plus Q2. Similarly, Q2 dash is equal to C2 by C1 plus C2 into Q1 plus Q2. Just by substituting the value, Q1 dash is your C1 by C2 plus Q2 dash. So this is the redistribution of charge between the conductors. The initial charge on this was your Q1. Now the charge on this your Q1 dash, and this is the value. Second point, loss of heat in this process. The loss of heat, we can say, if there is a difference in the energy in these two conductors before and after connecting with the wire, then we will say that difference of energy is nothing, loss of energy. So first, by energy conservation, so these two we can note down, and we will write the value of Q1 dash like this. Third equation I can say, from conservation of energy, from conservation of energy, we can write initial energy is equal to your final energy plus heat. It means UI, U final plus heat. U initial. Initial energy means in this position. So half Q1 square by C1 plus half Q2 square by C2. Final energy half Q1 dash square by C1 plus half Q2 dash square by C2 plus heat. Or this also can be written as half Q1 square by C1 plus Q2 square by C2 is equal to half common potential C1 V common square plus C2 V common square. The C1 plus C2 V common square plus heat. So heat is equal to 1 by 2 Q1 square by C1 plus Q2 square by C2 minus C1 plus C2, and V common is nothing, Q1 plus Q2 by Q1 plus Q2 by C1 plus C2 whole square. Now simplify. 1 by 2 C1 C2 C2 Q1 square C1 Q2 square minus Q1 plus Q2 whole square by C1 plus C2. This is equal to your half C1 plus C2 C2 Q1 square plus C1 Q2 square minus C1 C2 Q1 plus Q2 whole square by C1 C2 C1 plus C2. Now check it. 1 by 2 C1 C2 C1 plus C2, and simplifying this one, C1 C2 Q1 square plus C1 square Q2 square. Similarly plus C2 square Q1 square plus C1 C2 Q2 square minus C1 C2 Q1 square C1 C2 Q2 square minus 2 C1 C2 Q1 Q2 like this. So after simplifying, C1 C2 Q1 square C1 C2 Q1 square cancel, C1 C2 Q2 square, C1 C2 Q2 square will also cancel. Only left here C1 Q2 whole square, C2 Q1 whole square, and then this term. See. So heat is equal to your half C1 C2 C1 plus C2, then C1 Q2 plus C2 Q1 minus 2 C1 C2 Q1 Q2. So this is nothing 1 by 2 C1 C2 C1 plus C2, and this term will be written as C1 Q2 minus C2 Q1 whole square. This is the relation for this, or this further written as, if we want we can bring inside the C1 Q2 minus C2 Q1 by 2 times C1 C2 C1 plus C2. This is the heat on the developed during the redistribution of charge from this conductor to this conductor whole square. Now come to the next point here. See one example. From that example we may get better idea how to solve, or in that example if we want we can use direct relation also, and this relation can be replaced by in terms of potential also. Now the same expression can be replaced by in the terms of potential. So C1 Q2 and C2 Q1 whole square by 2 C1 C2 C1 by C2 as V1. V1 is potential on the first conductor was Q1 by C1 and second conductor was Q2 by C2. So we can replace the value of charge. So again heat is 1 by 2 C1 C2 C1 plus C2. Here C1 into Q2. Q2 is written as V2 C2, or we can write like this C1 Q2. The C1 Q2 means here C1 C2 into V2 minus C1 C2 into V1 whole square. Then we can take C1 C2 outside. That become your 1 by 2 C1 C2 by C1 plus C2 into V1 difference V2 whole square. In terms of potential, this can be written in this form, and in terms of charge, this can be written in this form. So anyway, we can write the expression and we can calculate the answer. See one example. From that you may get much more better idea how to use this relation. See one example. The question is that let two spherical conductor of radius R1 is 5 centimeter and R2 10 centimeter having charge 2 into 10 power minus 6 coulomb and 4 into 10 power minus 6 coulomb respectively, having charge this much. See, these conductors are very far away. These conductors kept very far away. So find the amount of heat developed when these conductors are connected with a conducting wire. Connected with a conducting wire. So here two spherical conductors are given. So what we can do, either this relation or this relation we can use to determine the heat. Direct formula we can use. No need to go through the whole derivation. So first we would like capacitance. So one of the capacitor have capacitance C1, and since it is spherical capacitor, spherical conductor have capacitance your 4 pi epsilon naught into R1. So 4 pi epsilon naught value your 1 by 9 10 power 9, and R1 value your 5 centimeter, 5 into 10 power minus 2. This is your farad. So C1 is written as 5 by 9 into 10 power minus 11 farad. Similarly, C2 is your 4 pi epsilon naught R2. So this is your, and R2 value your radius your here 10. So this will be your 10 by 9. So 10 by 9 into 10 power minus 11 farad. These are the value of C1, C2, and their charges also given, Q1 and Q2. Q1 is 2 into 10 power minus 6 coulomb, while Q2 is 4 into 10 power minus 6 coulomb. These are the charges. Just substitute the value. So heat is your C1 Q2. C1 Q2 value your C1 is your 5 by 9 10 to power minus 11 into Q2 4 into 10 power minus 6 minus C2 Q1 10 by 9 10 power minus 11 into Q1 2 into 10 power minus 6 whole square by 2 times C1 C2. C1 C2 will be your 50 by 81 into 10 power minus 22, and C1 plus C2. C1 plus C2 will be here 15 by 9 into 10 to the power minus 11. Now simplify this. See, so what we are getting here, 5 by 9 into 4, 20 by 9. This is 10 into 2 by 9, 20 by 9. These two will cancel, so it is your 0. It means what has come here, there is no loss of heat. No loss of heat indicate the initial and final. It means when these two conductors are connected, so these two conductors was initially at same potential, as well as so finally also, since initially these two have the same potential, because of the same potential there is no transfer of charge from one conductor to another conductor. That's why there is no loss of heat, so no flow of charge. We can check it from here. No flow of charge. So see, this is your spherical conductor of radius R1, and this is spherical conductor of radius R2. See the potential here, and charge on that is given your Q1, and here charge is your Q2. To see the initial potential of this, V1 is equal to your Q1 by C1, and V2 is equal to your Q2 by C2. See here, V1 by V2 is equal to your Q1 by R1 into R2 by Q2. See the ratio, Q1 by R2, Q1 by Q2 1 by 2, while R2 by R1 2. So this is your 1 by 2 ratio into 2 by 1, it becomes your 1. So that gives us कि V1 is equal to V2. It means initially these two are at same potential. So even though we have connected with a conducting wire, being a same potential, so no charge will flow. Since the charge is not flowing, that's why the total heat comes here 0. So this is the way by which we can solve the problem.